guys, it's Andy, and today we're going to start something a little bit different. Something called integrals, also known as antiderivatives. And what does this mean? Well, it's basically a derivative, so, we'll take the derivative of x squared, so 2x. Except we're going in reverse. We're going to somehow go from this to that. So, to start this off, what do they look like? Not what are they. I just told you what they are. Well, they look like this. There's an integral symbol, which is actually in my title sequence. It looks, if I were to, try to do it neater, it would look a little something like that, but usually I just do the funky ass like that. Then it's got a function right here, and then it's got a dx right here, which just tells you you're doing it with respect to x. There are a couple more meanings of this, and we'll examine that in the next video, but for this video, I'm just going to show you how to do them. And speaking of how to do them, well, we got a basic rule. There are several rules for differential calculus, which I'll explain to you later, but for today, we're just going to focus on the basic rule, and that's how you do something like x to the nth dx. So, if we think about how we do derivatives, let's say we got x squared. Well, how do we do this? We just bring this down, and then 2x, and then we do 2 minus 1. So what we're going to have to do derivatives, well, let's think. How do we get x squared out of this thing? Well, the way we do it is we can add a 1 here, and then we get 2x squared, but that's 1 too many x squared, so now we gotta divide it by 2, and that goes away, you get x squared. And so that's basically the rule. You get integral of x to the n dx. If you integrate this, it's going to be x to the n plus 1 over n plus 1. So you can think of this as 2x over 1 plus 1. And there's a letter right here, c. Well, what is c? C is the constant of integration. And you're probably thinking, well, what the hell does that mean? Well, I got an example right here because I thought you would ask that. So let's say we got this function right here, x to the third over 3 plus 7. And let's do the derivative of this, not integrating. So that's going to be 3x squared over 3. Take away the 3, you're left with x squared. And now we do derivative of 7, which is 0. So you see how when we got a derivative of something, you're going to lose some fidelity. Like this 7 basically turned into a 0. It's no longer accounted for. If I were to try and integrate this function, just x squared dx, I would get x to the third over 3.
2 plus 2 is 4, minus 1, that's 3, quick maths.
And there's no 7 over here. So the c acknowledges that there could be something there that you're missing. That's why it's called the constant of integration. It stands for something that you may lose during the process of integration. So, and now we got a few examples. So, whoops. We'll start off with one that we just did. Integral of x squared. Let's make that x to the third. Alright, so x to the third dx. So we're going to do x 3 plus 1 over 3 plus 1 plus c. And that's going to be x to the fourth over 4 plus c. And if we derive this, well, let's see. 4x to the third over 4. Get rid of that, you're left with x to the third plus c. And that works. It checks out. And now we got, what happens if we got a fraction? Well, it gets a little tougher. Not too much. And we got a multiple up front too. So it's going to be fun. So let's just do 4x to the 3 halves plus 1 over 3 halves plus 1. We can simplify this. 4x to to the 5 halves over 5 halves. And you're probably thinking, well, that doesn't look quite right. You got a fraction on the bottom, so how do we deal with this? Well, you should have been taught that you just, when you
go to divide a fraction, reciprocal and multiply it.
So 4x to the 5 halves times 2 over 5, get 8x to the 5 halves over 5. And that checks out. We can do the derivative of this to just make sure that works. So let's see. 8/5 x to the 5 halves. Alright, so multiply the 5 halves over here times 8 over 5. Cross this out, x to the 3 halves. And you get 4x to the 3 halves. And that's what we started with. And what about this one? Cosine. Well, we know that if we derive sine, we get cosine. This is one where we don't necessarily need to know the power rule. We can just say, oh, we know what the derivative of sine is, and it's cosine, so why don't we just go backwards? So the derivative of this is just sine x plus c. Did I forget it? Yeah, I forgot it up here. Oh well, rectified. And that's all we're going to do today, but just in the future, we're going to, well, first we're going to figure out what other uses this dx has, what integrals are useful for, and then we're going to learn a technique called u substitution, which is useful for different things which may not be easy to integrate. They might look a little unfriendly, and then we'll learn a couple things that you'll probably be taught in calculus too. So, I'm Andy. Peace out. These are integrals. Bye.
Yo. Big Shaq, the one and only. Man's not hot. Never hot. Skitty cat cat. Boom. 2 + 2 is 4. -1, that's